Greetings students and welcome back to class. Today we are going to be proving the double angle identity for sine, cosine and that of tangent. So if you have been wishing to know how to prove this double angle identity, stay tuned as we drill you through the procedure. So the double angle identity for the three trigonometric functions sine, cosine and tangent can be proven by using the sum and difference identity for sine, cosine, and tangent. So if I want to find the double angle identity for cosine, for example, I will use the sum identity for cosine. Cosine of A plus B is equals to cosine of A, cosine of B, minus sine of A, sine of B. So if I want to prove the double angle identity for cosine, I will have to assume that these two variables are equal. So I'll have to say let B equal to A. So this angle B becomes A. So I'll have cos of A plus A. Remember B now is A. Is equals to cos A. Instead of cos B now, I'm going to write cos A minus sin A. Instead of sin B, I'm going to write sin A. So I have cos A plus A is 2A. So cos of 2A is equals to cos A times cos A is cos squared A minus sin A times sin A is sin squared A. So this is one identity for cosine of 2A. Cosine of 2A has this identity. Now, remember from the Pythagoras theorem, you have a relationship between cos squared and sin squared. You know that cos squared A plus sin squared A equal to 1. This is the Pythagoras identity for trigonometry. So I can make cos squared A the subject by sending sin squared A across. So I'll have cos squared A is equals to 1 minus sin squared A. So if I take this identity and place it in here, I'll have cos 2A is equals to, now this cos squared A is 1 minus sin squared A. So I'll have 1 minus sin squared A minus sin squared A. If I simplify, I'll have cos 2A is equals to, so minus sin squared A is minus 2 sin squared A. So this is another identity for cos 2A. Cos 2A is also equals to 1 minus 2 sin squared A. Now, instead of replacing cos squared A here, what if I make sin squared A the subject here and then replace it in this identity? So from here, if I make sin squared A the subject, so sin squared A, I will send cos squared A across. So I will have 1 minus cos squared A. So sin squared A is 1 minus cos squared A. And if I take this identity, cos 2A is equals to cos squared A minus sin squared A. And then replace 1 minus cos squared A in place of sin squared A. I will have cos 2A is equals to cos squared A minus, now sin squared A is 1 minus cos squared A. So I'll have cos 2A is equals to cos squared A. Negative 1 times 1 is negative 1. Negative 1 times negative cos squared A is positive cos squared A. So if I simplify this side, I'll actually be adding cos squared A plus cos squared A. That's 2 cos squared A. And then I'll have minus 1. Now, this is another identity for cos 2A. So cos 2A has 3 identities, and we can write that in terms of a piecewise function. So if cos 2A is a function, then it has 3 identities. The first one is cos squared A minus sin squared A, which is this. The second one is 1 minus 2 sin squared A. And then the last one is 2 cos squared A minus 1. These are the 3 identities for cos 2A. And this is how each of them can be derived. So let's derive the double angle identity for sin 2A.